Hey, this is Mel Strong, and this lecture is on the carbon cycle and more about greenhouse gases. So this is a continuation of the greenhouse gas lecture, so if you haven't watched that, watch that one first. And one of the things I'm going to be doing is talking about how carbon moves around in different reservoirs around the Earth. And so I'm going to use some illustrations that I made that are on my website or on Learn if you're one of my students, and I'm going to illustrate them. Feel free to print yours out and illustrate it the same way. We talked about how last time in the last lecture that there are several greenhouse gases. There's a bunch of greenhouse gases, and some of them are really strong. But of all the ones that we worry about, CO2 is the number one gas that we're concerned about, just because as humans we produce more CO2 than anything else by far, okay? And so we worry about methane, we worry about nitrous oxide, but we really worry about carbon dioxide because we just emit so much of it. So that's what this lecture is about. It's mostly about CO2. And so we talk about where the CO2 is, and in the atmosphere, it's in the form CO2, but it can actually, that CO2 molecule can move to different locations, like maybe the ocean or maybe in a plant. And it's no longer in the form of CO2. It can change to a different molecule. So we keep track of the carbon part of the CO2. So when we talk about the carbon cycle, ultimately what we're trying to get at is that CO2 is in the atmosphere, and something is putting it into the atmosphere, something is removing it from the atmosphere, and it's being stored somewhere, but it's not necessarily always in the form of CO2. It could be some other carbon molecule, okay? So to start out with, what we're going to talk about is something called the reservoirs of carbon. Okay, this is where the carbon is. Okay, where is it being stored around Earth? And I'm going to use a unit here called the teragram, and we abbreviate it as TG. Oops. Okay, a teragram, 1 teragram is 1 times 10 to the 12th grams. And what that would mean is you'd have to move the decimal over 12 places. So for example, if I had 3 teragrams, that's the same thing as 3 times 10 to the 12th grams, which is the same thing as 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros, right? Put some commas in there. And the thing is, this is such a giant number, like you can't really wrap your mind around what that even means. And it doesn't matter, because the point of doing this is to show relative sizes of which reservoirs are bigger and smaller. But they're going to be in this unit of teragram. So for the numbers we're going to write down, remember, just add 12 zeros to everything if you wanted to write out the number. Okay, so the carbon we are concerned about is the carbon in the atmosphere, and it's in the form of CO2. And that number is currently about 829 teragrams. Okay, now by comparison, if you added up all the carbon of all of the plants in the world, you get about 600 teragrams. Okay, so these are, if you look these numbers up, you'll get slight variations on this. So these are kind of mutually agreed upon numbers, more or less, right? Okay, then in the soil, because soil, there's a lot of living and dead organic material in the soil, and that has a lot of carbon in it. Soil is about 2,000 teragrams. Okay. Now the ocean, there's a lot of carbon in the ocean, and it can be in a couple forms. It could be in the form of dissolved gases. Oops. So what that means is anytime you have gas sitting above liquid, there's exchange between the two. So there's CO2 dissolved in the ocean, just like CO2 is dissolved, say, in a soda. Okay, so some of it is in the form of that. Some of it is in the form of organic matter. So in other words, anything living in the ocean. So dead or alive, it's got carbon in it, okay? So add it all up, you get about 38,000 teragrams of carbon in the ocean. Now notice so far that that reservoir is so much bigger than anything else we've written up here, okay? That's just gigantic. Okay, so there's a lot of carbon in the ocean. Now, this diagram I made here shows carbonate rocks down here. What is carbonate rocks? Carbonate, a lot of times we have this compound called calcium carbonate, and a lot of organisms have this in their shells. So if you find a seashell, a clam shell, for example, it's going to be some version of calcium carbonate. And there's that carbon that's in this molecule. Well, when that animal dies, sinks to the bottom of the ocean, gets buried, that carbon is now buried in this, what we call carbonate rocks. A lot of it is microscopic organisms that you actually can't see. These are little microscopic plankton that float in the ocean. They have calcium carbonate skeletons, even though they're single cell microscopic organisms, and they die, they settle to the bottom. They make this carbonate mud that gets buried. And so a lot of carbon ends up getting buried in these carbonate rocks. Now here's the confusing thing, is that a lot of these carbonate rocks are no longer in the ocean because they're spread all over the planet on different continents where the ocean used to be. So we don't have time to go through the geologic history of all this, but there are many times in geologic history where, for example, the United States was covered in a shallow sea. And so we have lots of carbonate rocks all over the country, all over the world, that are not in the ocean anymore, even though they used to be in the ocean. So if you live around Albuquerque, you look up at the Sandias, you see these little horizontal stripes at the top. Those are carbonate rocks. Those used to be at the bottom of the ocean. The ocean wasn't up there. Those rocks were down below sea level at one point. Okay. Add up all the carbon in all the carbonate rocks in the world, and you get a pretty gigantic number. About 80 million teragrams. Okay, so that number dwarfs the one we just wrote. So most of the carbon in the world is tied up in these rocks, which again started out in the ocean, but they may no longer be there. And then the number 2 reservoir is carbon in the ocean itself. Now, we also have, in my little picture here, we got fossil fuels, right? And so we can break that up into, let's see here, we got coal. It's about 3,500. Oil, about 230. Natural gas, about 140. And other forms of fossil fuels, about 250. And you add this all up, and you end up with greater than about 4,100 teragrams. Okay, so let's compare these numbers. By far biggest, by far biggest in the rocks, but let's just leave those aside for the moment because that carbon's pretty much stuck there. The carbon in the ocean is the biggest reservoir by far. The carbon in the atmosphere is the one we worry about the most because this is related to the greenhouse effect. Notice how much carbon there is stored up in fossil fuels compared to the amount that's already in the atmosphere, right? So there's way more waiting underground that we as humans could potentially burn and use and turn into the atmosphere, right? Turn into atmospheric carbon. Okay, so this is sort of a simplified look at the reservoirs, where the carbon actually is. I'm going to start with another diagram just like this, and we're going to talk about processes that are going on here. Okay, so for this next diagram, we're going to do something about fluxes. Oops. Okay, and a flux, in this case, flux is something that's in motion. Fluxes, in this case, is carbon moving between reservoirs. Okay, so the last one was reservoirs. Where is the carbon being stored? Now we're looking at how is the carbon being moved back and forth between some of these reservoirs, and that's what a flux is. Okay, so we'll start with some that you probably already know. So you learned, for example, back in your days in biology about photosynthesis. Okay, so the general formula for photosynthesis, the general reaction is plants take CO2 and they take water and they take light and they produce glucose and oxygen, right? This is what photosynthesis is all about. This glucose molecule, if I were to write this out and balance it the way that a chemist would like, I would have 6 CO2s, 6 waters, and then I have this glucose molecule, 6 oxygens. Okay, so the 6 is that's just to balance it. When we talk about the carbon cycle, I said earlier that we're following carbon around and we're worried about CO2 in the atmosphere, but it can change its form and be in other molecules other than CO2. So here's an example of what I mean by that. The carbon was in the atmosphere as CO2, okay? And then the plant puts it into plant stuff, plant matter, glucose. Our carbon just changed reservoirs. It went from the atmosphere to the plant, right? So that's a flux. We're taking it out of the atmosphere, we're putting it into some biomass, okay? So as long as a plant is photosynthesizing during the day, it's removing CO2 out of the atmosphere. Okay, so what I'm going to do is draw these fluxes in different colors. So vegetation, I'm going to draw with a green arrow, and what's coming in from photosynthesis is about 123 teragrams per year. Okay, so this is photosynthesis. Okay. Now, the plant continues to live when the sun is not up, because plants, like us, have to respire. So even though they are producing oxygen during the day and they're using up CO, they're pulling CO2 out of the atmosphere during the day, there's a secondary process that's going on 24 hours a day, and it only goes on, it's the only process that goes on during the night, but the plants are doing it 24 hours a day, and it's called respiration. Respiration is what we would call breathing, okay? We're breathing in oxygen, we're letting out CO2, that's respiration. We do it, animals do it, plants do it, and so if we write out that formula for respiration, it's basically the opposite of what we just wrote for photosynthesis. Okay, so we would have the glucose plus oxygen. We'll get some heat out of this reaction, some CO2, and some water vapor. And so now what's happening is the carbon that is in the glucose is being transferred back into the carbon that's now in the air, right? So this was in the plant, this is in the air, this is in the air, okay, this is in the air, right? So photosynthesis, we take the carbon out, we put it into glucose. Respiration, we take the carbon out of the glucose, we put it back in the air. It's basically backwards. Now, we're doing the same thing. Even though we are not plants, we are still taking a carbon from glucose and we are exhaling CO2, right? Okay, so, but just to focus on plants for a second. So what that means is there is this photosynthesis that's removing carbon from the air, but then there's respiration that is putting it back, So this is plant respiration. Okay, so 50 teragrams is going back out into the atmosphere. So the net that plants are doing here is they're bringing in more carbon than they are producing, as long as the plant is growing. So this is a worldwide average for all the vegetation on Earth. Okay. Now, speaking of respiration, down here in the soil, there is a lot of things that are living in the soil. I mean, you have the root systems are respiring, you got microorganisms that are respiring. So there's respiration going on in the soil, and that is contributing carbon to the atmosphere as well. So I'll use a purple color here. And that is about 70.4 teragrams per year. Also, so let me just put down soil. This is respiration and fire. So fire is the same reaction. This is also the same reaction for fire, except fire, it happens faster. But when you're burning a plant, you're taking the carbon from the plant matter, reacting with oxygen, getting CO2 and water vapor. Okay, so respiration and fire is the same reaction, just respiration is slow, fire is really fast. So if you take all of the naturally occurring respiration in the soil and all the naturally occurring fire, you get about 70.4 teragrams per year going out back into the atmosphere. Well, now I've got a little farmer here and a campfire and whatnot, and this is to simulate what humans do. We call this land use, right? So if we cut down trees, we put up a parking lot, we build houses, we make roads, we plow fields, we burn things down, that's collectively called land use, okay? And land use, there's actually, we could break it down further. Like if I'm a farmer and I plant crops, those crops will pull down the CO2 out of the atmosphere. But when I take everything into account, so the planting of things plus the burning of things, all of that combined, it turns out that we add about 1.1 teragrams per year. And this is called land use. Okay, land use. All right. We will come back to this in a second, but let's talk about the ocean. So one of the things I said about the ocean a minute ago is that there's gases that are going both directions in the ocean. So you have gases going into the ocean, and you have gases leaving the ocean. So I'm going to call this gas exchange. And so you have the experience that if you take, say, a soda and you twist the top, and then CO2 comes bubbling out, right? That CO2 is dissolved into the liquid, right? So you can take gases and you can dissolve them into liquids, or pour a glass of water, set it down, come back the next day, you'll see little bubbles on the inside, right? That's gas that is coming back out of the liquid. So this is happening with the ocean. There's gas going into the ocean and there's gas coming back out of the ocean. And what's going into the ocean is about 92.3 teragrams per year. And what's leaving the ocean is about 90 teragrams per year. Okay, so there's a little more going in than there is coming back out, and we'll come back to that in a minute. And then finally we have our fossil fuels here. As we burn fossil fuels to, like we said in the last lecture, mostly generate electricity, transportation, we are adding about 7.8 teragrams per year. Okay. All right. So we talk about sources and sinks. What does that mean? Sources is we're adding CO2 to the atmosphere. That's a source. A sink means we're taking it and we're putting it away somewhere, underground or in a rock or in a plant. That's a sink. Okay. So we've got sources and sinks. All right, going each direction. So if we, and by the way, this is simplified. There are many other smaller ones. I'm just trying to paint the big picture here. So the next diagram is going to be what is the net result? What is the net result of all of this? All right, so for this one, we're looking at the result of the previous diagram of fluxes. So if I take all those fluxes, the sources and the sinks, and I do the math, and we see where ultimately are the changes occurring. Overall, every year, there's about 2.6 teragrams of carbon going into the world's vegetation. Okay, so every year that goes by, we're adding more carbon to the world's forests, to our farms, anything that's growing. Okay. Now, if you remember from just a minute ago, we were looking at the last diagram. We had over here that there was two arrows going up and down from the ocean, and the net is that there is about 2.3 teragrams per year going into the ocean. All right, so there's gas exchange. Some goes into the ocean, some comes out of the ocean, but there's a little more going in than there is coming out. And so the net is at 2.3 teragrams per year are going into the ocean. We'll talk more about that in a second. And then the atmosphere is gaining about 4 teragrams per year. Okay, now this is the number. This is the thing that we're worried about the most. Okay, we're worried about what is the effect of these increasing CO2 levels, right? And that's what you've been reading about in my class. This is what we're going to keep talking about. But let's talk about this one first. What does it mean to keep adding this much carbon into the ocean every year? Like, what does that do? So one of the things that it does is if I take carbon dioxide and I react it with water, I will get a compound H2CO3, which goes by the name of carbonic acid. This is a weak acid. CO2 in the presence of water turns into a weak acid. If you had a really bubbly soda and you're trying to drink it out of a glass or something, you may have had the experience once in a while that your eyes burn a little bit, like when it's super fizzy. That's carbonic acid. So every year we're dumping 2.3 teragrams. Remember, that means times, you got to add 12 zeros to the end of this, is going into the ocean. And that CO2 that goes into the ocean, you may have read in our textbook that it's a good thing that the ocean is taking up some of the CO2 because that means there's less of it for the atmosphere. But it's a bad thing because we're making the ocean more acidic. The oceans are, over time, are becoming more and more acidic because of this. Now, why is that a problem? So let me show you a couple pictures. So when you think of a coral reef, this is probably what you think of. They're in shallow, usually warm water, a lot of very colorful organisms, and I want you to notice that it's in pretty shallow water here, maybe a meter or two below the ocean surface. And there's a lot of different organisms that live on a coral reef. So we've got sea anemones here, we've got starfish, we've got sea urchins, we've got all kinds of things. But they're all living on this big mound in the background, And the mound itself was built by these little organisms called corals. And these look like plants, but they're actually colonies. Each one of these has a bunch of little tiny individuals living inside. And the coral is each one of these little animals. And they secrete a calcium carbonate shell, essentially, that binds them all together into like this giant apartment complex. And each one of these guys is an individual. So corals are related to jellyfish. They have these little stinging tentacles. They sit there and they do this, waiting for something to float into their mouth. They're a pretty simplistic organism, but they're important because this calcium carbonate house that they're making forms the basis for where all those other organisms that you saw earlier are going to live. Now, even though corals are animals, they have living inside their tentacles these little single-cell photosynthetic bacteria called zooxanthellae. Okay, so this is what they look like. So there's one of the tentacles of the coral, and you see these little green spots. Each one of those green spots is a single-cell photosynthetic organism that generally cannot survive on its own outside of the coral. So this is kind of confusing because the coral is an animal, but living inside the animal are these little plant-like things that are photosynthetic, and they're producing energy that the coral itself is using. Okay, so they have this symbiotic relationship. Nothing's going to eat the zooxanthellae because they're sitting inside this stinging little tentacle here, and the coral itself gets some energy from them. In order for this to work, the coral has to be about a meter below the ocean surface, right? So if the coral gets out of the water gets out of the water, that's not good. The coral dies. If the water is too deep, there's not enough photosynthesis. That's also a problem. So they like to be about a meter or so below the surface. Well, when a coral gets stressed, for reasons that I don't think are totally understood, the coral will reject all of those zooxanthellae, and they turn white. And this is called coral bleaching. So this coral right now is stressed. What would stress it? Higher temperatures will stress it, or if the ocean becomes more acidic, that will stress it out. And so as we have been making the ocean more and more acidic and warmer in some respects, we're seeing more and more bleaching of corals. And so in some places we see this big extent of coral bleaching. Now these corals, again, this is the first stage on their way out. So they will reject the zooxanthellae. If conditions improve, then they will come back and things are okay. If conditions continue to deteriorate, then the corals will die. Okay, so not all these corals in these pictures are necessarily dead yet. Here's some before and after pictures of corals that are now bleaching, and we see big chunks of coral reefs around the world starting to do this. This is the bad sign. It tells us that the oceans are now becoming inhospitable for the corals, and the corals form the basis for these coral reef ecosystems. Here's one that's finally dead. So this one has bleaching, and then conditions never got better, and the corals finally died here, and now they kind of turn this dark color. So let me see here if I go forward. Here's an example where some coral, this is the corals bleaching just starting to happen. You see a big bleaching event here the following year, and then later the corals are all dead and turning this dark color. So that is one of the reasons why we worry about the amount of carbon going into the ocean. We're producing carbonic acid. That is stressing out the corals. The corals form the basis for these coral reef ecosystems, and we're seeing these big bleaching events. So 100 years ago or so, scientists thought that we might be adding carbon to the atmosphere, but no one had actually measured it. And so people speculated that, we think today people talk about global warming like it's this new idea, but you can find scientific papers 100 years ago where they were speculating that this could happen. But we didn't really have any good measurements of carbon dioxide in the atmosphere. So finally in the 1950s, a guy by the name of Charles Keeling decides that he's going to build a machine that's going to measure carbon dioxide. And he's going to build a machine that takes a measurement like every day, and we're going to start monitoring it over the long period and see if it changes. So in order to do this, he needed to find a spot that was away from cities, that was, hopefully up in the atmosphere. He wanted to get the cleanest air sample he could. And so he decides that he's going to do this on the big island of Hawaii. And so the big island of Hawaii has two volcanoes, Mauna Loa, Mauna Kea. They're both over 11,000 feet tall. And so at that time, there wasn't a road up to the top or no electricity or anything like that. This is a pretty big project, but what he managed to do starting in 1957 is he built an instrument and he put it on the top or near the top of one of these volcanoes, Mauna Loa. And here's a picture of what it looks like up there. You're actually above, there's a cloud layer that forms over the ocean. This is stratocumulus we talked about earlier in the semester. You're above the stratocumulus on most days. And this is a sign that's up there today. So it's at 11,141 feet. And right now there's a lot of equipment up there. But back then, the very first thing that they were measuring was CO2. So he builds this machine, he turns it on in 1957, and he lets it run, and it runs a couple of years. And he looks at his data for a couple of years, and he finds that there's this very odd pattern where the CO2 goes up and then goes back down again, up and back down again, up and back down again. But as it's doing that, there is this very slow rise over time. Okay, so we're going to talk about this. This graph is called the Keeling Curve. There's no Nobel Prize in meteorology or climatology or environmental science or earth science, but if there was ever a Nobel Prize in this field, this graph would get it first. Okay, it's such an important graph, it actually has its own bronze plaque. And I don't know of any other graph that has its own bronze plaque. Okay, the Keeling Curve. So we're going to study the Keeling Curve because it is so fundamentally important to environmental science and what we're talking about here. Okay, so we're going to have a look at the Keeling Curve. And on the axis, on the x-axis is time, and on the y-axis is CO2. Now, you'll see, for example, on this one, it says parts per million. Okay, so there's not much CO2 in the atmosphere, but we have a way of expressing it. So if I had 3 parts per 100, okay, we would call that percent. And we use this symbol, right? So the math would be 3 over 100. Okay, that's percent. There's another symbol that you're probably not familiar with, where if you had 3 parts per 1,000, that's called per mil, and it has 2 little circles, and you would do 3 divided by 1,000, okay? If I have 3 parts per million, the way I write that is 3 ppm, and if I did the math, 3 divided by a million, okay? So on this graph that we are going to look at here, the y-axis is usually in ppm, parts per million. All right. So a couple years after Charles Keeling turns on his machine and he starts to get data, this is what he sees. He sees this up-down pattern. Let me try to focus. And he also sees that this up-down pattern is gradually increasing, and he knows that this is pretty significant. So there's 2 things going on, and we got to separate them out. First is, what's causing the up-down pattern. Okay, now, on Earth we have what we call deciduous trees. These are trees that in the spring they bud out, and as you start to grow, there's a growing season, the leaves get bigger. In order for the leaves to get bigger, the plant has to pull CO2 out of the atmosphere. Okay, so throughout the summer, the deciduous plant, deciduous tree, whatever it is growing, and is pulling carbon dioxide out of the air, and it's making, from photosynthesis. So then, coming to the fall, the deciduous tree loses its leaves. Leaves fall to the ground. Now, that carbon that it took out of the atmosphere, a lot of it is now laying on the ground in the form of dead leaves. And little microorganisms are munching away and digesting that, and that carbon goes back up into the atmosphere. So in a normal year, for a particular, if you think of just one deciduous tree, in the spring and into the summer and the growing season, it's taking CO2 out of the air. In the fall and the winter, it's actually adding CO2 back into the air because it's dumped off all of its leaves. Okay, so now, imagine instead of one plant doing that, imagine all the plants in the world doing that. So, because the seasons are reversed, when we have summer or let's say spring in the northern hemisphere, our plants in the northern hemisphere are starting to bud out, and they are sucking down CO2 out of the atmosphere. But at the same exact time, the plants in the southern hemisphere are experiencing fall, and their leaves are falling off, and that's adding CO2 to the atmosphere. So the two hemispheres, the plants in the two hemispheres, balance each other out. But when you look at the two hemispheres, what you see is that there's way more land in the northern hemisphere than there is in the southern hemisphere. Okay? So, what does that mean? That means that there's more plants in the northern hemisphere than the southern hemisphere. So that means that when we're talking about competing seasons, the plants in the northern hemisphere are the ones that actually are in control of the carbon in the atmosphere because there's more of them. So even though these, if the hemispheres were perfectly balanced, if there's the same amount of land in each and the same amount of plants in each, as one was losing its leaves and the other was budding out leaves, the two effects would cancel each other out. But they don't cancel each other out because we've got more plants in the north. Okay, so thinking about that then, if we consider this up and down is being controlled by what the plants in the north are doing, right? So let's say we'll start in the fall, and the leaves fall off in the fall, and they fall on the ground, and that returns CO2 to the atmosphere. So that means that where we see CO2 increasing, that's starting in the fall, and it continues throughout the winter in the northern hemisphere. In the northern hemisphere. Okay, so the seasons I'm writing are northern hemisphere. Okay, so CO2 gets returned, and then we finally get to the spring, and things start to bud out, and as they do, they start pulling CO2 out of the atmosphere. So we get into spring, and as we go down this way, this is the growing season, and into the summer. And then it repeats again. Fall, into winter, etc. So this up and down that we're seeing, that's due to plants. And it's due to the plants in the northern hemisphere because we have more of them. Okay, so that's the first thing Keeling notices. But the second thing Keeling notices is perhaps more important than that, which is that this whole pattern is on the way up. And he realizes, even after just a few years of data, that this slope is due to us, to humans burning fossil fuels. So this is the human CO2 contribution. that's adding on top of what the plants are doing. So you can kind of think of it like this. If there was a world with no humans, we would expect that it would do this. It would cycle with the seasons of the northern hemisphere because again of the plants. But it's doing this instead. Because every year we are adding more to the atmosphere. And so every year we progressively add more and more and more. So here are some data from Hawaii, just the last few years. Okay, and you can see there's the red, the up and down, those are the seasons. And then this black line is sort of a mathematical average over time. And if I go forward one more here. So here's, for example, just the last few measurements of the last few days when right before I recorded this. We have surpassed 400 parts per million now for a couple of years. And as seasons, right now we're going into the northern hemisphere spring, so we should actually expect some of these numbers to start to go back down here a little bit. This is what it looks like today up there. There's a lot of instrumentation. They're measuring all kinds of stuff up here at the Center for Stratospheric Research is what they called. And so I actually went there a few years ago to do some research of my own. And this building right here, that's the building that has that bronze plaque on it. So here's another picture of it. It's this right in here. And this is really off limits to the public. It's just scientists, super nerds walking around here. But if you go inside this building, this is what it looks like. And there's this box right here and this really old chart recorder. And you open it up and there's a piece of plexiglass here. And this is one of the original this is one of the original machines that Charles Keeling made. It's technically not the first one because the very first one I guess got taken apart, but it's essentially the first one. So all the scientists, they are like, oh my God, they get so excited, and you can see my reflection taking a picture of it in there. But this is the first CO2 monitor. Since Charles Keeling put that in on the top of Hawaii, we've been putting them in all over the world. And it's the same pattern everywhere. It's that same up, down, but climbing CO2. So one thing we'd like to know as climate scientists is how much greenhouse gas was in the atmosphere in the past, whether it be CO2 or methane or whatever. So we have Keeling's machine that's been taking measurements since 1958. But how much CO2 was in the atmosphere, say, 100 years before that, or 100 years before that? So there's a couple ways you can do it. Some people have found sealed old bottles with air in it and analyzed that. So maybe you find an old bottle from 150 years ago. You can analyze the air in there. But further back you go, the harder it is. And so one of the ways that we do it is if you find a place that has been frozen consecutively without ever experiencing any melting, that you can actually find trapped atmospheric gas in the ice. So snow itself, fresh snow, so if you're a skier, think of like some fresh powder, that's like 90% air. But then after the snow sits on the ground for a while, it very slowly starts to recrystallize. And that fluffy snow kind of gets gritty and granular. And then eventually it turns into something called firn. And if it's a place that never ever actually melts, what'll happen is those nice fluffy snowflakes eventually turn into solid ice. And the air that fell as snow gets encapsulated as little bubbles. So this is what it looks like. So the little bubbles in this ice are little trapped pockets of atmospheric gases from when this ice first formed. So if this piece of ice is 1,000 years old, then the bubbles in there are little samples of 1,000-year-old atmosphere. So this only works if you have a place that never gets above the freezing point, right? Stays frozen all year round. So there's two main places that we can do this. One is Antarctica, and the middle of Antarctica never melts, and middle of Greenland. Now there's also some places you can go and do this on the continent where you have glaciers year round. Now, those glaciers are disappearing, but people are still trying to sample them. So if you want to do this, you get yourself some Russians, because they really like the cold. They go out to a place like Antarctica, and they set up these geodesic dome tent things, and they drill down into the ice. So this is a specially designed drill to drill down into the ice and remove what we call an ice core. So they're trying to recover the ice without destroying it. And this is what an ice core looks like. So they'll drill down thousands of feet and keep removing ice. And the ice that they remove, when they pull it out and polish it, you can see the individual years. So in a place like Antarctica, you only get a couple of centimeters of snow a year, but it just never melts. And so each band is a year, and the bubbles that are preserved in each band have a little sample of the atmosphere from that time, whenever that ice formed. So what you can do is, if you drill down enough, you can go down thousands of years, you can extract air thousands of years ago, and they store this ice in these giant warehouses that are kept below freezing. So each one of these tubes has an ice core in it. Now let's say you're a climate scientist, and you're like, I would like to find the samples of the atmosphere 50,000 years ago. So what you do is you go to one of these facilities and you find ice that's 50,000 years old. And there's a whole setup with saws and everything. Everything in this warehouse is kept below freezing. And you cut out the ice you're interested in, and you seal it in glass, and then you melt it, and then the bubbles come out, and it's sealed in this glass that you put it in, and then you extract the gas out and you analyze it. So using this technique, we can actually recreate the atmosphere all the way back several 100,000 years. So Antarctica has been below freezing for several 100,000 years. So in this graph, what they've done is they've reconstructed CO2 parts per million. And here is today. Now this graph was made a few years ago. So today the CO2 level is higher. It's kind of like up in here now. But they went back. Now this graph goes back, it says 400,000 years, and then it says for 650,000 years, atmospheric CO2 was never higher than this level. So we can, with Antarctica, we can actually go back pretty close to 1 million years before you run out of ice. And when we extract the ice and we analyze the gases, what we find is that for the past 1 million years, we've never seen CO2 as high as it is today. Okay? Now, you see these big patterns, right? So here, the CO2 was pretty low. We were in what we would call an ice age. Here, the CO2 was higher. So Earth was warmer. Then we've got another ice age, warmer. These are natural cycles, and there's changes in the Earth's orbit that cause this. Okay, so we're not worried about that. Like we know what does this. What we're worried about is this, that we now have more CO2 in the atmosphere than the Earth has seen in the last 1 million years, or maybe more. And the question is, what is the Earth going to do? How is the atmosphere going to respond? We can also look at other greenhouse gases. So this is years ago. I think it got cut off as time before 2005 when this was made. And they're looking at methane. And now they're looking at ppb, parts per billion. They're getting it out of the ice. So you can see from about 10,000 years ago to pretty close to the present day, there wasn't a lot of variation in methane. Remember, methane is a pretty strong greenhouse gas. There's not much of it in the atmosphere, but it's a pretty strong gas. And then starting, and they're zooming in here is what they're doing. Starting about 1900 or so, we see a big uptick in methane. So methane is probably higher now than it's been in the past million years. Or if you remember from the last lecture, another strong greenhouse gas is nitrous oxide. Again, parts per billion. There's not a lot in the atmosphere. You see some error bars, so there's more uncertainty in the measurements. But again, back 10,000 years ago, the amount of nitrous oxide stayed pretty constant until we get to, again, about late 1800s, 1900, and it starts to take off again. It's higher now than it's been in the last 100,000 years, or last million years or so. So one of the things they've done is reconstructed what we call the pre-industrial atmospheric concentration. So when we talk about the industrial age, that roughly correlates to like 1800-ish or 1850. People have different definitions of industrial revolution, but sort of when humans started with steam engines and burning a lot of coal. So 1850, we'll just use that as a number. CO2 is about 280 parts per million. So in other words, if the Industrial Revolution didn't happen and all of the things that humans have done since then didn't happen, we'd expect the atmosphere to have about 280 parts per million. And as we just saw a few slides ago, it's currently over 400. And they've also established some other ones, methane, nitrous oxide, a few others. But these numbers here, the pre-industrial amounts, that is what the concentrations should be. And then these numbers here are what they currently are. And actually, this is already obsolete, so they're even higher than what is shown here. So, in conclusion, whether you look at CO2 or methane or nitrous oxide, we've got more greenhouse gases in the atmosphere right now than the Earth has seen in the past about million years, maybe more. What's going to happen? And the short answer is we're not totally sure. So we know that there are natural variations in greenhouse gases. So we saw the CO2 go up and down in the past, but it's never been as high as it is today. So one of the questions is, what is the climate system going to do? And we're going to talk more about this in the future lecture, but one of the big worries is we're not totally sure what it's going to do. We know things are warming up. We can predict how they're going to warm more in the future, but could there be something else that's going to happen? And we'll talk more about that in a future lecture. All right, thanks.